Welcome to the Global Composites Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites, with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Survey, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
The Dassault Systems 3D Experience Education Center of Excellence in Advanced Composites is the result of a 7-year partnership between Purdue University and Dassault Systems. It is expected that this new level of engagement will bring significant benefits to the two partners and to the global society as we work together to bring the advantages of the digital age to society. Together, we will advance the digital enterprise by developing the human talent essential to this new paradigm and by utilizing the 3D Experience platform to exercise digital twins of complex composites manufacturing and performance to demonstrate the power for simulation of phenomena that are understood today only by empirical experiences. We will work together to introduce those concepts to a wide range of industries within the advanced composites community, from the original equipment manufacturers to the supply chain industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered. Next, I will ask Dr. Pipes to introduce our distinguished speaker today.
I am delighted to introduce Pascal Hubert, the Werner Group Chair in Sustainable Composites Manufacturing at McGill University. I first met Professor Hubert in 1999. Not long after he finished his PhD at the University of British Columbia, when he and his wife, Dr. Isabelle Perry, joined NASA Langley Research Center under the National Research Council program. Pascal and I shared a small office with only 2 desks as furniture, and we worked with the NASA engineers in the area of nanocomposites. To say that Pascal became my teacher in those years is an understatement, because 17 years of university administration had separated me from the new ideas in composites manufacturing, and it was Pascal who filled the gaps for me. It was a great partnership. Pascal Hubert's research interests focus on the development of the next generation of process modeling tools for advanced composite materials. He also studies the mechanical and physical properties and processability of new revolutionary nanostructured composites, also known as nanocomposites. A combination of experimental and computational techniques are utilized by Pascal to reach these goals. He also teaches the mechanics of deformable solids, aerospace structures, processing of composite materials as his teaching requirements at McGill. He's the director of a very large cluster that regroups 70 researchers and over 500 graduate students working in the field of polymers and composites research. He has over 300 refereed journals and conference publications in the field of composite materials, and he has planned and led collaborative grants with industry like Bombardier, Boeing, Bell Helicopter, Pratt & Whitney, Airbus, Safran, Ford, and over 200 small enterprises, manufacturing enterprises. And these are all working on the development of composite materials processing and nanocomposites. I am delighted to introduce my colleague, Pascal Hubert.
Thank you very much, Dr. Pipes, for this introduction. And welcome everybody to this presentation on sustainable manufacturing of composite materials. So before I start, I would like first to show you this beautiful picture of our planet Earth. And I would like also to show you today's vital signs of that planet. So we see here that carbon dioxide level are at about 416 parts per million, and they are rising. Global temperatures are rising since 1880. We have our Arctic ice and ice sheets that are shrinking and are increasing over the years. So clearly there's something going on our planet. And the main cause of these changes are the level of carbon dioxide, or referred as greenhouse gases, that you can clearly see here that they are increasing very rapidly since 1950 level. So what is the source of this change? And obviously, it's a large part coming because of a human activity on the planet. We have the population is increasing, obviously, but our human activities, as you can see here on this chart, with our agriculture, our waste, our industry, takes about the quarter of the emissions of those greenhouse gases. But the energy that we consume for our industries, our transportation, and our buildings takes about 73% of these greenhouse gases. So there's definitely something that needs to be done. So what can we do? So there's several solutions that we can attack this problem. So we can address more energy efficient transportation and things like that. So be more efficient with the consumption of the energy. We need to do a better job maintaining and taking care of our waste. We have to obviously go towards renewable energies. We need to reduce methane emissions, and also we need to increase our fuel efficiency. And composite materials, as I will show you, can help in many of these aspects on efficiency of our vehicles and so on. As far as methane emissions, well, perhaps we should eat less meat, and that could also help. So to look at the composite solution, I would like to share with you a truly Canadian application, which is the evolution of the hockey stick. So you know hockey in Canada is very popular, so I thought I would show you how the design of the hockey stick evolved and how composite play an important role. So if you go back at the origin of the game in the 1900th century, the hockey sticks were made out of wood. They were essentially solid cross-section of wood, and they were heavy, and and therefore sometimes not too performant. And then the hockey stick evolved in the 80s to an aluminum shaft design, which was then a hollow structure, much lighter. And one of our most famous players, Wayne Gretzky, really pushed for that type of stick. And then around 2000, the hockey stick was designed in composite material, mostly carbon fiber epoxy. And there was truly an advantage of switching to composite because it enabled great flexibility in the design. As you can see on this picture, you could tailor the flex of the stick and therefore having a very light stick with extremely powerful shot. So it's interesting now to look at how the hockey stick evolved and look at how our material use over the years evolved. And I'm showing this very famous Ashby chart that shows the different ages of materials. And we can see that in the early days, wood was a very dominant material. And then we went through the age of steel where metals were dominant. And today, we are moving towards a much more even distribution of materials. And we can clearly see that the composites are growing in use and in application. So there's going to be a lot more composite in the future. So the composites, as we all know, and we saw a lot of examples throughout these webinars, have great capabilities. So we can design aircraft that are much more fuel efficient. We can integrate them into the design of cars that use electrical energy. We can use them to make windmills so that produce these renewable type energies. We can also use them in applications where you wouldn't think of, like music instruments. We can make these super powerful sailboats, and also we can integrate them into our architectural design. So they are truly an enabler of achieving all these goals of making these structures more efficient. But they also have their issues, and we've heard a lot about it in the other talks in this series, that they can be difficult to process because we are actually engineering the material as we engineer the part, and therefore often they are hard to make, and they need a lot of trial and error. Now we have more tools to reduce the problems during manufacturing, but it's still not easy. They also have sometimes complicated failure modes, and therefore it's a lot more difficult to design very efficient structures and safe at the same time. So they are a bit more challenging than designing with metals. And also they are more costly compared to other materials, which therefore often put a break into their application compared to more conventional materials. But the true dark side of a composite material is their sustainability. We see that making composite parts uses a lot of consumables that often are landfill, they are not recycled. The end of life management of composite is really not mature. We still landfill a lot of structures. We don't know what to do. They do not degrade. We have no mean of using them and reusing them. So this is a real problem, and there's a lot more work that has been done in the last 20 years on this topic, and we need to continue this work. So what is the problem? What is it so difficult with composite? Well, one of the issue, and I'm showing this chart, which summarizes most of the manufacturing process in composite, is that the beauty with composite is that you can really tailor the material. So you can use a wide range of reinforcements from short to continuous, and then a wide range of polymers from thermosets to thermoplastic. And you have all of these processes that have been developed to make parts with these materials. So you get a wide range of different mix and match of materials, which makes them very to recycle or to reuse. So that's part of the problem. Also, if you look at the way that we make composite parts, I mean, a lot of the processes use material placement that are, in fact, coming straight from the fashion industry, where you take materials from rolls, you cut patterns, and then you then assemble them to make your part. That consumes a lot of material, and there's our waste that we still don't know what to do with. Now, we have a lot of development in automation of the process where you place the fibers where you want. This is great. Those processes are really taking a lot of attention. There's a lot of developments, but they're also very costly and they might not be as robust. And therefore, a lot of companies cannot use them today for their application. When we look at the way that we cure our material, when we have thermosets, we often use ovens or autoclaves. They're not the most efficient system in terms of energy consumption. We also use presses and other techniques, but again, the management of the energy use to cure the composite can also lead to some huge amount of energy that is consumed. So I would like to show you here a little mark against another type of composite that is the oriented strand board, which is a composite made out of wood. And I was fortunate to spend 3 years in that industry, which I didn't know of, straight after my PhD. And I discovered a fascinating industry. And I want to share with you a little bit how they do it, and use that as maybe a target of where our advanced composite industry should try to go. So if you look at an oriented strand board production, you start off with wood, which is a renewable feedstock, and the wood is then processed into chips. The chips are then aligned with very little waste because even the smaller chips are integrated into the panel. And then these preforms, if you wish, are then pressed into large hydraulic presses like you see here. And then they are cut, inspected to look at the quality. And what you notice on these pictures is that you don't see any human being in the plant. In fact, there's one person that is in a control room and is monitoring all of this manufacturing automatically. So this is very far from what we do in our industry. We have some applications where the process is automated, but very few. So we have a lot of challenges for our industry to become more sustainable. And I'm just showing this as a very schematic illustration of a footprint that we need to address. And I've divided the footprint into 4 issues: energy, cost, waste, and time. And what I would like to do is to show you a couple of examples that summarize what I've done in the last 20 years. And I would like to maybe highlight a couple of key things that I've worked with that I think really contributed to this effort. So first, I would like to discuss processing science. And I'm going to not cover, I could spend a lot more time on that topic, but I just picked maybe 2 examples of what kind of technology that really helped us better understand the process in order to reduce the risk of manufacturing with composite materials. So the processing science is really trying to make sure that you end up with a composite that is fully impregnated, because that's the end of the day, you want all the resin to fully impregnate the fibers. You want to be able to make complex shapes, and you want also to be able to make these really nice integrated structures like sandwich panels without any problems. And then you have to play with a lot of different materials, different processing conditions, different tooling, different environment. And that could be complex. So how can we get a better insight of what's going on during the manufacturing of composite? The technology that I think really helps, in my opinion, the use of micro-CT. And this is really incredible because micro-CT or X-ray scan have been used for ages in the medical field to be able to look inside the human body. But using that technology and being able to look inside a composite material was, for me, one of the main developments. The ability to monitor what the material was doing during manufacturing was really helpful. And I want to demonstrate that to you. So I'm going to show you some CT scan of a composite prepreg, an autoclave prepreg. And I'm going to take it through a typical cure. Here we see the temperature in red, rising to the cure temperature. And in blue, you see the viscosity of the resin decreasing to the minimum viscosity that will allow the resin to flow. And we're going to look at images, micro-CT images at different stages, as illustrated by this dot, where we stop the process and look at the material. So if we look at the material in its initial state, you see a very porous material. It has been engineered for that so that we can evacuate all the air. And we see the fiber toes that are not impregnated and the resin film in light gray that is surrounding the material. So now we see after we apply vacuum for some time that we get rid of some of those macrovoids through the consolidation by the vacuum pressure. But obviously, there's still a lot of unimpregnated toes. As we increase the temperature and therefore decrease viscosity, now the resin can start to flow inside the toe. And we see that there are still some dry toes, but the area is shrinking a little bit. And at the end, when we get the full impregnation, we can see that the resin has infiltrated the toes. And now you can take these images and do some analysis, quantitative analysis of the dry toe area evolution with time. And that's what I'm showing here. So obviously there's some variability, but you can see the clear trend that those dry toe initially are quite large, but then as resin flow, it starts to come to zero. Now, through this great images, we can come up with a very simple model of the toe impregnation process by just assuming the toe to be a circular bundle where we surround it with resin and we just solve for the flow, the radial flow of the resin through the porous media. We have some wonderful work that has been done over the years on that topic, and we can integrate those analytical equations into and obtain a solution for the level of impregnation of the toe as a function of our material properties, the permeability, viscosity of resin, and so on, and our boundary conditions in terms of compaction pressure and bag pressure. Now, with this type of model, we can then run very simple simulation to look at, let's say, what is the effect of the resin degree of cure, in the initial degree of cure, on the impregnation process of that toe. And at some point where you see here that if you have initial degree of cures that are too high, which means that the prepreg would be staying out in the floor for a longer time, necessary to do like the layup, you might get some voids. And then you can see that by changing the heating rate during the cure, you can make the impregnation more efficient. And also you can have a little bit more robust system where you can tolerate a little bit more of out to get problems. So this kind of insights through the micro-CT led to a better understanding of the process, and therefore that could be used back to the production to guide what kind of manufacturing protocols could lead to problems. Another very interesting and challenging materials to process are those multi-scale composites. As Dr. Pipes mentioned, I did work a few years in the field of carbon nanotube composites and also with graphene to produce nanocomposites. And the idea here is to take those nanocomposites and combine them with scale fibers to obtain some multifunctional composites. But as you probably all know, in the literature, you find that it's very difficult sometimes to do this. You have issues with the dispersion of the carbon nanotube or the graphene. And the problem is that we can obtain a good dispersion to start with, but then during the process, we don't really know what's going on. And again, I found that the ability to visualize what is going on during the process gives you some good insight of what matters. And so the idea of just placing the nanocomposite on a hot stage and watching the evolution of dispersion during cure helps you to understand a bit what's happening. And I'm showing here the little video where you're going to see the carbon nanotube. As we increase temperature, they go from a nicely dispersed state to a not so good dispersed state, where you get agglomerates of the carbon nanotubes. And with these images, you can then do some image analysis. You can then look at the distances between the matrix and particle elements and come up with a very simple index that will give you the quality of the dispersion from a uniform dispersion to an aggregated dispersion. And so once you have that tool now, you can start really to look at what are the effects controlling that dispersion. And to just give you an example here, I have a profile of the resin with and without the hardener. So we raise the temperature. Without the hardener, obviously, the viscosity keeps decreasing. But with the hardener, you see eventually that it cures. Now we can compare those two materials and look at their dispersion index. And you can see that because we are capturing the video, we can calculate the evolution of degree of dispersion with time. And we can see that it starts off with a pretty good number, 90, but it finishes to a lower number. And once we have that tool, then we can do all kinds of analysis with different heating rate, different nanotube ratios, and so on. And we can start with maybe a process that leads to a lot of aggregated nanotubes, as you can see here on this image. And through some optimization, we can then obtain a much more stable dispersion of the nanophase. So these two examples just illustrate how, with the tools that we have today, the micro-CT, be able to visualize the process using specialized fixtures to monitor all the key process parameters during cure can give us better insight, having better understanding of the processing science, and therefore reducing the risk in our manufacturing. Now I want to jump to another idea, and it is the ability to repair. So if we can repair composite structures that are damaged, then we don't have to throw them away. And it's so important to also address the repair of structures, because in service, they will have issues. And in cars, imagine that you're running your car and then you have an accident, you won't be able to repair it. The problem with composite repair, it's not a very mature technology. If you look at a typical repair, you'll see a lot of bolts and rivets. Ideally, you want to be able to do bonded repair, but there's a lot of issues with bonded repair due to the scatter. The scatter in performance comes really in part with the uncontrolled processing variability. You do the repair in an environment sometimes that you don't control. Remember, you need to repair now a structure that is not going to be necessarily in a nice controlled environment. It could be on a tarmac, it can be in a city that is at 4,000 meters and so on, or you can be in a very humid environment. So we need to develop better, robust repair methods. We know that if we use, let's say, out-of-autoclave prepreg to do a repair, if we make the out-of-autoclave prepreg in the best condition possible, you get very low viscosity, low porosity, sorry. So we can control the process, you get good quality parts. As soon as you deviate from those conditions, let's say now you have another so good vacuum in your vacuum bag, you are in the moist environment, you cannot extract all the air properly. You start to see a degradation of the quality of the composite. So in a repair, this is what you're doing. You have a parent laminate that has a damage. You take the damage out, so you scarf, and then you put a patch. The patch can be pre-cured, or you can co-cure the patch on the part. And then we put an adhesive layer. So the challenge here is to really try to remove all the air from that patch so that you have no porosity at the bond line. One way of doing this is to play with to do something to the adhesive. And the solution that we developed was to do an embossing of the adhesive. And by embossing, you create these little evacuation channels that will allow air to escape. To show you how it works, we can compare a repair done with a film adhesive that is normal and then an embossed adhesive. And you can see here the two configurations for monolithic and sandwich. So first, let's look at the quality of a standard adhesive. You can see here the bond line. And then you have also, and you can see the porosity of the bond line, and the repair patch even has some porosity. If you look at the image of that bond line from the top of the laminate, you can see the different steps in the joint. And you can see from the micro CT and the X-ray, you can see all the porosity. With an embossing, you now managing the air evacuation, and you can now see the nice quality at the bond line, and even in the repair patch. You've reduced the porosity dramatically. And what is the advantage of this is that it's shown here. So let's say you want to inspect the repair for looking at maybe kissing bond, like weak bonds between the adhesive and the parent laminate. Well, if you have a lot of porosity at the bond line, you're just going to see this. On the left, you're going to see a lot of noise. You're not going to be able to pick these defects. With a clean, nice bond line, you're going to see those big circles that would be the kissing bonds. So those were artifacts that were placed in that bond line to see if you can detect them. So developing those more robust manufacturing techniques for repair is really important. And the scientific community is not really too excited about working on repair. If you look at the literature, it's very, very few papers, very few interest. A lot of it is developed by the manufacturers. But I think the scientific community could really help in that aspect. And I encourage, people to work in that field. Let's look at another method to make our process more sustainable is to work on reducing the energy required to cure part. And this is through heated tooling technology. So there's a lot of technology out there. Like if you go to GAC, SAMP, or CAMEX, you'll see a lot of companies that propose solution where they heat the tool and cure the part using heated tooling, rather than using, let's say, an oven or an autoclave. We've actually used a technology that was developed in Montreal, the MTI heating element. The way that it worked is that the heating element, was sprayed directly on the tool surface through thermal spray. So what you see on the image here, C is your tooling substrate, B is your layer of ceramic insulation, and A is your resistive coating or the heating element. And here you see a simple tool that was manufactured, like a small plate. And what you see is the underside of the tool. And what you do here is that you just place your laminate directly on the tool. The heating element is underside. So you're heating the tool, and you have a layer of insulation on top. It's really the concept of barbecuing your composite. That's what you're doing. In terms of heating efficiency, it's really, really good. If you compare the energy consumed to cure a part in an oven compared to those heating elements, you can have 60 to 90% in energy saving. So this is great. Obviously, there are some issues with designing the heating element and so on, but you can also develop methods to optimize the element for the specific part that you're producing. So this can be also a way to help even in traditional oven or autoclave process where sometimes the convection cannot reach certain areas of the part. You can have heating elements placed strategically to help. So I think this is a very interesting technology that we should push, looking at alternative ways of curing our composites. The next example I would like to provide is to deal with the waste. How can we reduce waste? Well, we need to develop more net-shaped parts. And there's a lot of efforts, and I want to share a little bit some of my own experience with this. So net shape can be achieved with short fibers manufacturing. Injection molding, we can make net shape part routinely. It's a fast, you can make very complex parts, but the performance is not really great. On the other hand, continuous fibers, as you know, are excellent in performance, but it's very hard to make net shape part. Processes are not that fast, and it's hard sometimes to make complex. So the idea is to look at these long discontinuous fibers, and sometimes they are referred as platelet composite or random strand. There's been a lot of work, and Dr. Pipes presented some of that in his presentation. So there's a lot of interest in this field, and I think we should really work on that. More people should be involved with this. Just to give you an example, this is the type of net shape part that we can make. It's just a simple bracket, but we have a feature here, a rib, that sometimes creates some problems in terms of the quality. Because when you make it in a mold that you see here, it's a cavity mold, so the rib will be on the top part of the mold here. And when you apply pressure, you might have problems maintaining that pressure during the process, and then you'll get some problems. You can control the heat from the top and bottom mold, but sometimes you don't know how to control it properly. So what you end up with are regions of high porosity, because at some part during the process, you lost contact with the mold and you had not enough compaction pressure. And the more complex the part is, the more it's going to be difficult to maintain this. So you need some tools to do that. So there's been a lot of work, and you've heard what was done at Purdue as well in that field. Doing simulation of those materials is key. You do the thermal simulation, so you know your temperature history, and then you can couple that with temperature-dependent properties of the material, their shrinkage, the modulus evolution, and then you can simulate how the pressure in the part changes and identify those regions of low pressure. You can also do residual stress simulation to look at parts' dimensional stability. The idea here is to use this simulation to guide you towards the design of the tooling and the process. To show you here the example of how you can play with the process, I'm showing you first the temperature profile of the top and bottom tool that follows the same trend. What you can end up with is a poor quality of the rib, even if you put more pressure, because putting more pressure will not help in that case. What you need to do here is to do a different temperature cooling profile from the top and bottom. And that was developed through the use of these models. Now, what you see here is that by just delaying the cooling down of the bottom part compared to the top part, you end up with maintaining this pressure and creating a very nice surface for the rib. So through this development of better process control and simulation aids, you can really now make these net shape parts. Now, one interesting thing that you can do with these net shape parts is to also combine with your short fibers, you can also or long discontinuous fiber, you can combine elements using continuous reinforcement that you can place strategically. And that in general will help and increase the performance and reduce some of the variability that we see with these materials. Another very interesting application of these hybrids is that you can design by placing continuous fibers in strategic places in the mold. Like here in this case, I'm showing a kind of prism laminate that we place right at the base of that rib. So then when the fibers are flowing in that rib, they will be guided by this flow control element. And what you end up with is, on the right, you'll see clearly that the strands or the platelets have really followed nicely the radius in that rib. And that led to a significant increase in resistance of that part. So again, designing these net shape parts with of discontinuous and continuous fiber element opens the door to a lot of possibilities. So that's a real good example of how we can move towards net shape manufacturing of a composite part. Now, the last section that I want to talk about, which is one that I've been working the last 6 years, is on the recycling business. How can we recycle composite materials? So let's look a little bit at and there's a lot of work, excellent work. There are companies today that can do this. So what are the approaches? So first, you can just use thermochemical fiber recycling so that you can reclaim the fibers out of the composite. And that can be done at an end-of-life stage or with manufacturing scrap. So what you do is you basically get rid of the resin. This often creates some issues at the fibers. You degrade the fibers a little bit, and you just throw away the resin, and that in some state is uncured if you take manufacturing scrap. And you often have to have large infrastructure to do this. Then the approach of basically just shredding the composite through a mechanical comminution will obviously degrade the fibrous properties. You get some kind of filler more than a composite that can be recycled. And you cannot recover a lot of fibers through that process. And finally, the other approach is to say, well, I'm just going to burn the composite and capture the energy. Well, this is one approach, but it's not considered recycling. So what I really concentrated my effort was on dealing with these uncured manufacturing scrap for pre-preg. As I explained in the beginning, our pre-preg comes in forms of rolls, and then we cut patterns. And so there's a lot of offcuts from the pre-preg ply cutter. There's also a lot of expired material, rejected material. These are all materials that have pristine fibers and matrix. We know their history and how they were stored and processed. There's very limited contamination. And more, it's going to be more expensive to dispose of these materials. So that's the kind of recycling that I was really interested to develop. Because the numbers can vary from 30 to 50% waste. So it's very significant. So the approach that we developed was to take these uncured pre-preg offcut and transform them into a recycled compression molding compound. So I'm going back to my chip idea here. To do so, you need to do some resin characterization, some flow experiments, so that you can design the right aging protocol for the pre-preg to get to this recycled compound. That's what I'm going to be showing to you briefly. So let's say that you want to do it without doing all of the of what I'm going to present. You're just going to take the offcuts, you're going to cut them and try to make a part through compression molding. You're going to get an ugly part. You're going to get resin fiber bleed, very poor quality with voids. It's going to take a long time for you to cure that material. And the material is going to be very hard to handle because you're going to deal with a pre-preg that is tacky because it's straight from the roll. Okay, so that's because the pre-preg were designed for an autoclave process. In an autoclave process, when you apply pressure, you're going to want the resin to flow and wet the fibers. So you want low viscosity of the resins to fully impregnate the part. And then the resin will be controlled because of the pressure used in the autoclave and the type of shape that you're doing. But when you try to do compression molding, what you really want is you want the resin and the fibers to flow together. You want to be in a shear flow mold, which is typical of high viscosity resins. So you want to go from this from the autoclave to the compression molding process. So this is done through pre-preg staging. So here I'm showing you a viscosity map and initial degree of cure. And the different lines represent different curing temperature protocols, low temperature to high temperature. So if you take an autoclave pre-preg, it's usually cured at 180 degrees Celsius, and it starts fresh, so very low viscosity and very low degree of cure. If you want to now increase the viscosity of the resin during cure, you will have to cure it at lower temperature. And that will take forever because the cure kinetics of that material is not optimized for low temperature cure. In order to have your shear flow behavior, you want to be in that range of viscosity. This is typical of the thermoplastic composites that are flowing by shear most predominantly. So what we want to do here is to take our pre-preg and stage it, B or C stage it if you wish, to a range of initial viscosity that will trigger the shear flow of the material. And it will be we'll be able to process it at lower temperature and in a much faster way. So with the help of these 1D flow compaction experiments where we place a composite, the pre-preg, into a mold and excite the flow in one direction, we can really observe the occurrence of that shear flow and try to find the best conditions in terms of what are the best staging conditions that we can get the most of more shear flow. And this is the type of result that we get from these experiments. So for different level of staging, that's the resin viscosity axis. So more staging, you'll have higher viscosity. You'll see the effect on the amount of shear flow that you get. So obviously in that range, the shear strains, the shear flow is very low, so it's not the best conditions. You need to be in that range here. So where you can see now values of shear strains that are higher. This is what we want to get. To find a good balance between the amount of staging that we need and the level of shear flow that we have, we will probably want to be in the range of 200 to 300 Pascal second for that material. So this is the kind of staging target that we're going to get. To show you how is this stage pre-preg or recycled pre-preg material perform, we're going to demonstrate the manufacturing of two complex parts. One that has a multi-rib and one that has different features, very sharp radii, thickness changes, and even a hole here that in the middle. So this is how we place the recycled compound. And then just to show you what happens if you don't do the staging, the top images are these two parts with pre-pregs straight from the roll that were cut, no staging. And as I said before, it's not going to work because it cannot flow properly. With the right staging protocol, now we can make very nice parts with very high quality. And that's the key of being able to use these offcuts, is to bring them to the right level. Now, obviously, there are some challenges, as you can expect. A lot of the pre-preg comes with the backing film that needs to be disposed and taken care of. Obviously, there's some risk of having little contamination. You can have sometimes mixture of different pre-pregs, and can you combine them and use them as a compound? There's a lot of questions to be answered. When you design complex shape parts, net shape, you have to also look at the possibility of knit line formation, and you can clearly see it on this image. But this is true for any net shape part, so you have to deal with these issues. But this recycling is very promising, and there's companies out there that are actually using that approach, and truly this is a part of the solution. Now, I would like to show you also some other initiatives that will help towards sustainability that are not necessarily my work, but other ideas that are going on. So the first one is additive manufacturing. Obviously, it's a field that is allowing you to make net shape parts, and it's really growing at a very high rate. There's a lot of interest there. So this is definitely going to be a technology that will help reducing waste. The multifunctional composite, where you can combine structural and electrical capabilities of the material, will be also a very valuable application, making our cars even lighter. Self-healing materials, again, in the idea of dealing with the repairability of the composite. Self-healing materials are also a very interesting solution to the idea of increasing the sustainability of the material. The use of biocomposites, so it can be biofibers, bio-based resins, really important. Always being careful with using, proper feedstock and not creating more problem by treating all these biomaterials, and you have to do the right analysis, life cycle analysis, but this is part of the solution. And recently, just in terms of more the way that we meet, the way that we teach, as you saw initially, a lot of our impact on our green gas emission is through the travel that we do. And with this last year, with this pandemic, we were forced to actually stay home and work from home. And that had an impact on the green gas emission. Can we reinvent a little bit the way that our community interact, how we teach? And in fact, I'm showing a picture here of a class that I taught in 2006 with Dr. Pipes. And in those days, we were doing it through a video conferencing, not through Zoom, and it was kind of cumbersome, but it worked, and it was quite an experience. And now we've done this routinely for the last year. What about our conferences? Can we organize? It's important to meet in person, but also their planning should be done so that it has a minimum impact on our travel. So I want to finish with this picture. You all recognize Greta Thunberg. She was in Montreal. This picture was taken in Montreal in 2019. She was here for a big march for the environment. And I took all my lab with me, and some of my students came with me, and there's a picture of them. And it was a really emotional event for me, like to be surrounded by so many people marching for the environment. And I think this is something that we all should be involved with. So I would like to acknowledge first the wonderful students that worked for me over the years. This is their work that I presented. They're amazing. The ability for us as academics to train these young people and watch them grow is what makes me live every day. So they are part of all of this work, and I would like to acknowledge them. I'd like to acknowledge also the collaborators that I have with my other academic collaborators and research institute collaborators that I've had over the years, and our industrial partners and government partners that help. In Canada, we are lucky to have very good support for research for composites, so I would like to acknowledge that. And I would like also to thank 4 persons that were very instrumental to where I am today. First, Professor Boukili from École Polytechnique. He introduced me to the wonderful world of composite back in 1989. And then Dr. Poussartip from University of British Columbia was my PhD advisor. And a lot of the way that I run my group is because of his training. And Dr. Pipes, obviously, you heard that we met at NASA, and that was a chance for me to interact with him. He really opened the door for me to a lot of initiatives, a lot of ideas. I think it was mutual and the way that we help each other. And finally, my father, Joseph Hubert from Université de Montréal. My dad was always here when I started my career, and he really helped me in these early days as a young academic to navigate through all the university and grant and system. And without his support, I wouldn't be here today. With this, I'd like to answer any of your questions, and thank you for being with me today. Thank you.
Dr. Hubert, thank you very much on behalf of all of the audience and all of us as panelists hosting this. We thank you very much for your inspiring talk, and have time for a couple of questions here. A number come in, of course, as you would expect around in a conversation on sustainability around natural fibers. Would you comment for a moment on the relative strengths and weaknesses of natural fibers and what you would expect going forward with both carbon fiber and perhaps methods to reduce the energy footprint of carbon fiber, the relative proportion of carbon fiber to natural fibers, and so on, and what you see going forward, obviously across a number of industries?
Yeah, this is a very good question. And in fact, my experience with natural fibers are quite limited, but my colleague here at McGill, Professor Lestard, has a lot of experience with these fibers. And what you just mentioned is there. Like there's ways that you can combine natural fibers and advanced fibers, and that has some benefits. The natural fibers, you have to have natural fibers of very high quality, and so that also has some impact on how you harvest them, how you produce them. So I think the natural fibers have their place and don't need necessarily super high performance. You maybe just need a roof for your house, and you can just take natural fibers with some local materials that you find. There's a lot of applications out there, so I think they have their place for it.
Very good. Well, thank you very much. Again, thank you for your presentation. And we remind the audience of the upcoming presentation, Nancy Sotos, on June 3rd, and we look forward to seeing you all then.